In today's tutorial, we will discuss the Arbuzov reaction and how to construct an energy diagram following the course of the reaction. As the first example, we will focus on this primary bromide. This should react with triethyl phosphide, the typical reagent in the Arbuzov reaction. And what will happen? The phosphine is a nucleophile. Nucleophilic substitution will take place clearly according to an SN2 process. Since a SN1 process with a carbenium cation is not feasible in this case, a primary carbenium ion is just not stabilized good enough. So, nucleophilic substitution according to SN2 will give a salt and now the bromide is a weak nucleophile, but in this structure we have a rather good leaving group. Nucleophilic substitution takes place again by an SN2 process, and we will get to this product interesting for Wittig type reactions and as byproduct the ethyl bromide. So for the construction of the energy diagram, let's say here we have situation A, this is situation B, this is situation C, and since this reaction proceeds very easily already at room temperature or a bit elevated temperature, we can assume that the overall energy decreases from here, from A to B to C. So let us just put in here the energy level for A, somewhat lower for B, and the final product C even lower. SN2 reaction takes place via a transition state. First transition state, second transition state, and this is an appropriate energy diagram for this mechanistic scheme. Let us go on with a second example. And let us change a little bit here in the starting material. This time a tertiary bromide with a vinyl group, actually a propenyl group, attached. In this case, the direct attack of the triethyl phosphide at the tertiary center is sterically hindered, there might be an SN2 prime process take place. That means that the phosphine will attack at the double bond. SN2 prime will lead to the same product as we will see with an SN1 process. And SN1 means, well, a stabilized, mesomerically stabilized carbocation can be formed, this one, as a reactive intermediate. So let's call it reactive intermediate Ri. And now the triethyl phosphide can attack. It will preferentially attack at the peripheric carbon. Leading to this intermediary product. Here we call that situation A, this is situation B, and the final SN2 step will give us this product. So, situation C. Let's construct the energy diagram. What has changed is that we have a reactive intermediate in between. And the only thing we have to change, therefore, is here. There, the energy level of the reactive intermediate and this is the appropriate energy diagram. Let us have a look at a third example. Now we have the bromide at a secondary, sitting at a secondary carbon and a quaternary center in alpha position. Again, the attack of the triethyl phosphide is sterically hindered. So we can assume that an SN1 process or an SN1 type process will take place, forming the secondary carbocation in the first step. This is still an equilibrium reaction step. But now one methyl group can migrate. It's a typical Wagner-Meerwein rearrangement. And this tertiary carbocation can then be trapped by the triethyl phosphide. It will be attached to the same side as the hydrogen, because that side is sterically less hindered. And the final step is again the typical final step for the Arbuzov reaction, the SN2 reaction, forming ethyl bromide and the target product. Sorry. This one. So that means after situation A, we have the first reactive intermediate, here the second reactive intermediate, again then here situation B and the situation C. That means in our energy diagram we have to change a little bit. After reactive intermediate 1, we get a second reactive intermediate. Since this is a tertiary carbenium compared to a more stable tertiary carbenium compared to the secondary carbenium ion, it is on a somewhat lower energy level. You come to situation B and over another transition state. Here we have also transition states. We get to situation C. Thanks for listening.